So in the very end of last lecture, we talked about multi-arm bandit. There are two objectives, and objective one is we want to identify the epsilon optimal arm. In terms of the mean reward, we want the arm we identify is at most epsilon worse than like the optimal arm. In the second objective, we're saying we want to achieve low regret. In a sense, we define a regret to be T times Ri star. That is the total reward if you're gonna receive, if you always put the optimal arm, and subtracted by the expected reward you're gonna receive by the algorithm, where IT is the arm, the agent pool at T's time. So I think we say the major difference is in the first objective, we just eventually want to find the epsilon optimal arm. We don't really care about in the middle, like during the learning process, what do we pull? Like we can just pull arbitrary bad arms. As long as in the end we find epsilon optimal arm, this is good. On the other hand, objective 2 seems like more difficult. Okay, so it's like a harder objective, which not only says you want to eventually find some optimal arm, because eventually you want this regret to be small. You almost you kind of like you already make sure like you want this IT to be approximate to be I star. You not only want eventually you put the right arm, but also in the middle, like during the entire learning process, you want your arm put is also like nearly optimal. Like even if in the earlier phase, like you don't want to put some terrible arm, like suffer significant regret. So this is like more difficult objective. And we need to do more work to balance the trade-off between exploration versus exploitation. Exploration in the sense, eventually we want to find epsilon optimal arm so that our asymptotic performance of the regret is good. And exploitation in the sense, during the entire playthrough, we should not just play some arbitrary bad arm so that I will suffer a lot of regret. So that's why it's like a big balance between those two. So we will first talk about the conversion between these two objectives. So for a lot of times, we can do some conversion. But we will see later, this conversion actually will suffer some looseness if we do a lot of conversion. This is online to batch conversion. So this is lemma 1. Although we we say this conversion in the multi-arm bandit setting, but this conversion can also be extended to reinforcement learning set setting very easily. It's a very straightforward extension. Okay. So we will talk about the relation between the regret guarantee and the sample capacity of identify epsilon best arm. So the conversion stays in two ways. The first is if algorithm A has a regret C times T to the 1 minus alpha. Okay. So we talk about why this we want the regret to be this form. Essentially because if the reward is bounded by 0 to 1, then this regret is always in 0 to T. So anything linear in T, regret is like trivial, it's not very interesting. So we always want some sublinear regret, that is 1 minus alpha, where alpha is some constant in 0 to 1. So regret bound is always going to be like this sublinear in T. This is like non-trivial regret. If we have an algorithm A that has a regret of specific form like this, C times T to the 1 minus alpha, where C is some absolute constant, then algorithm A will find an epsilon optimal distribution of R. In C over epsilon to the 1 minus alpha samples. So basically, T to the 1 minus alpha regret will convert to the sample complexity that is 1 over epsilon to the 1 over alpha, to the power of 1 over alpha. And on the other side, conversely, if algorithm A finds epsilon optimal R, this can also be a distribution. It doesn't matter. It doesn't matter it's a single arm or it's a distribution. In C times epsilon to the minus beta samples, then we can use algorithm A to achieve regret. Two times C of 1 over 1 plus beta times T to the beta 1 plus beta. Okay. So we'll talk about the exponent later. But the most important thing is if we forget about the constant thing, so what do we say is any sublinear regret T to the 1 minus alpha can be converted to some sample complexity that is 1 over epsilon to the power of 1 over alpha. And on the other hand, if we have some sample complexity that is 1 over epsilon to the beta, then we can convert it to a regret that is T to the beta over 1 plus beta. Okay, the other constant doesn't really matter. You can just switch to some other constants. So this result kind of like holds for any alpha and beta. So we can convert the regret that is T to the 3/4 or convert the regret that is square root T to something like sample complexity. So we will first look at some particular examples. I think a lot of times we will handling the square root T regret. So for example, if we have some algorithm that achieves square root T regret, in that case, alpha is equal to 1/2. And this implies we can achieve something that is 1 over epsilon square, because alpha is just 1/2. So this will imply some sample complexity that is 1 over epsilon square samples. And on the other hand, we can use the second rule. That is, if we have some algorithm that achieves 1 over epsilon square samples, we can convert it to a regret guarantee. And in this case, it's clear this beta we just choose beta to be 2. And now we notice we no longer get back square root T. What we get is T to the 2/3. And we note in the regret that the worst case regret is t. So in terms of power, square root t regret is actually better than t to the 2/3. The closer you get to t, the worse you get the regret. So this is like worse than square root t regret. So we kind of like, we note when we do the conversion, we convert the regret to sample complexity and convert sample complexity back to the regret, like in this black box manner. We don't get back the original result for free. I think the biggest reason is, as we already said, this regret is the harder objective. So we kind of like when we convert a harder objective, which inherently require we to balance the exploration versus exploitation, to something we only require exploration, and then we kind of convert it back to the original harder objective. We kind of like we lose something during this entire process. So this conversion is done like not freely. Like we kind of like we lose something during the entire conversion. So I just want to make sure you understand this conversion kind of like give a connection between two objectives. But what I also want to say is like when you do this conversion, you kind of like you lose something in terms of like strength of the objective and all the rates.
What do you mean by conversion? Like, what does it mean to go from UT regret to 1/4 squared samples?
So we will actually talk about proof, and that will be much clearer. So basically, whenever I have done an algorithm, I already achieved this regret. Then this algorithm we can use this algorithm immediately to achieve this sample complexity. And conversely, it's also the same. Like if I have an algorithm that already achieved this sample complexity, I can very easily like modify the algorithm to achieve this regret. Okay, so this lemma is only talk about the rate conversion, and we still need to provide an explicit construction. Like when we have algorithm A achieve this regret, why this algorithm already achieved this sample complexity? Like, so we need to do the proof. Okay, any question about the claim and the qualitative results? Okay, no problem. Let's just do the first one. This conversion actually is pretty straightforward. So by first claim, for the conversion from regret to sample complexity, we first write by precondition of regret. We know by the definition of regret that is equal to T times R star, Ri star, subtract by T, summation T from 1 to capital T, Rit. And this is less or equal to, because we have the precondition of the regret, we know this is less or equal to some constant times T to the 1 minus alpha. So this implies that we can divide both sides by t and rearrange the terms. So this implies that 1/t summation t from 1 to capital T, Rit, is greater or equal to Ri star subtract by c over t to the alpha. So we notice this is more or less what we want. So left-hand side can be viewed as expected reward if I pull arm according to some empirical distribution d hat I, where this d hat is uniform over all the arms I have pulled so far. So I1, I2, till it. That is if I uniformly pull an arm, this like induce a distribution. And if I just uniformly pull through this distribution, and this is corresponding to left-hand side, we calculate. So this is an epsilon optimal distribution over arms. So only thing we need to do is we make this thing to be epsilon, so that we guarantee this d hat distribution is epsilon optimal. And then we can just solve this, which we get t is equal to c over epsilon to the 1 over alpha. Okay. So that's why like when we have like this many of samples, we can achieve epsilon optimal R. Okay. I think the first part is relatively simple because, as we said, regret is just by definition a harder objective than samples. So whenever we achieve the regret, all we need to do is just divide it by t and like do an average, and we already achieved the epsilon optimal arm. Like we already get the optimal arm. So we'll do the second claim. Second claim requires slightly more work because, like we say, the regret is a harder objective, while sample complexity is like an easier objective. So we want to convert an easier objective to a harder objective. So that's why we need to lose something and we need to do a little bit more work. The strategy we're going to do is called explore then commit. Explore then commit means I will first spend c times epsilon to the minus beta round to find epsilon optimal arm. So this is by precondition, we know this is the sample complexity of arm A. So we'll first just spend this much round to find an epsilon optimal arm. And then we will spend the remaining round, that is a t minus c times epsilon to the minus epsilon, to always pull this epsilon optimal arm. So it's very intuitive. Explore then commit. That is, in the first phase, I will just do exploration. I will do whatever the algorithm do, and to find the best arm, to find the approximate best arm. And in the second phase, I will just commit to this approximate best arm. So I'm just always going to pull this arm. So we'll calculate what is the regret achieved by this algorithm induced by A. So the regret t, we can compute that is less or equal to, in the first phase, we spend this many rounds, c times epsilon to the minus beta. And because in the first round, in the first phase, we kind of treat this algorithm as a black box. We don't really know whether this algorithm has done any like exploration versus exploitation trade-off. So we just assume the worst case where this algorithm probably just do some random exploration, or I don't know. Like in the worst case, probably the regret is going to be 1 at each round. Okay. So at each round, maybe at most, I will suffer loss 1. And in the second phase, I have this many rounds. And because we know every time I'm already commit, I pull the arm, which is guaranteed to be epsilon optimal. So that means in the second phase, in every round, I will at most suffer epsilon regret. Okay. So we can just simplify this expression a little bit. And this is less or equal to c times epsilon to the minus beta. And plus, in a lot of cases, this t will be significantly greater than this c times epsilon to the minus beta. So we just ignore the second term, ignore the thing we kind of like subtract and provide an upper bound. This is plus t times epsilon. And finally, we just pick the epsilon that minimizes the regret. That minimizes this regret, which is this epsilon is equal to c over t to the power of 1 over 1 plus beta. And we get the regret that is equal to 2 times c to the 1 over 1 plus beta times t to the power of beta over 1 plus beta. And this finished the proof. Yes?
Wait, sorry, what are those terms in the regret going to again? The
Oh.
epsilon non-optimal, the non-optimal arm is the C epsilon 2.
Yeah, so the explore and commit algorithm contains two phases. The first phase, I just use the algorithm A to find the epsilon optimal arm, which takes this many rounds by the precondition of algorithm A. And the second phase is I just commit to this optimal arm. So in the second phase, every round I pay a regret of epsilon. And in the first phase, I don't really know what the algorithm A is doing, so I just assume the worst. We know every round my regret is at most 1. Because regret, you can also write this regret in terms of equal to summation t from 1 to capital T, and which is I star subtract I t. So we can talk about calculated regret per round. So each round I will suffer regret at most 1. And in the later phase, regret is at most epsilon. Is this clear?
How does that end up being the same formula?
This one equal to this one?
Yeah.
This summation is the same, and this is just t. So summation of I star is a fixed thing. So all you need to prove is ti star is equal to summation.
Is that a minus or a product between T and I star?
Product. This is like the total reward we receive by the optimal arm.
Wait, why do you want to pick epsilon and push it back? Like, is there a reason for it?
This to pick epsilon to minimize this term. You can think. So you can think this regret is basically c beta is something positive. So this is a c over epsilon to the beta and plus t times epsilon. So you can think when we increase epsilon, this term go up, and this term goes down. So there is some epsilon term which minimizes this entire thing, and you can take derivative to equal to 0, and which you will find this is equal to this. Okay, those are all good questions. Okay, if no other questions, I guess we will start talking about the algorithm for multi-arm bandit and the regret and the sum complexity for those algorithms. Those are just, and so far we haven't talked about any algorithm for multi-arm bandit. We just talk about how we're going to convert the two different objectives. And later on, we will just purely focus on regret because this is like the standard notion people use for online learning. And we know regret is stronger than sum complexity. So whenever we want sum complexity, we can just use this conversion to convert it back to sum complexity. So the first algorithm we will introduce for the multi-arm bandit is called epsilon first algorithm. Epsilon first algorithm essentially just use the explore then commit strategy. Only difference is in this conversion, we will actually say we will first spend this one to use algorithm A to find epsilon optimal arm, well, here we will be very specific. We just do some random exploration in the first phase. So the first phase, we will first pull each arm. For n times. And obtain an empirical estimate. I hat, that is equal to summation of j equal to 1 of n I j. This ij denoted the random reward that we receive. For arm I at j's pool. Okay, so j is the index of the index of pools we get for arm I, and we use the empirical average that divided by 1 over n, divided by n. So essentially, the algorithm is very simple. I just pull each arm n times, and I use the average as my estimate of the mean reward for each arm. And then in the second phase, I will just play I hat equal to argmax I of I hat. That is, I will just pull the arm that has the highest estimates in the first phase for the remaining steps. So first, we'll talk about essentially this algorithm works because essentially we can say when n is large enough, our estimate for each arm is like very accurate in the first phase. As long as, like for example, if it's epsilon accurate. And when it's epsilon accurate, then we can essentially do this explore then commit to get reasonable regret. So in the theorem 1, we say for n equal to c times iota of epsilon square, where this iota is equal to log a over p. We have with probability 1 greater or equal to 1 minus p. The maximum difference across all arms between our estimate and the true mean is less than epsilon. Okay. This more or less implies that we just pay number of samples, sample complexity that is n times a, because this is the number of pools we need for each arm. So the total number of samples is like n times a, which is equal to this C A iota over epsilon square. We will find the epsilon optimal arm. Okay. Because after this many samples, we guarantee every estimate is close to the optimal by epsilon. So whenever I do the maximum over my estimate, I'm guaranteed this is epsilon optimal. Okay. Any questions about this theorem? Yes?
A is the number of arms? Or?
A is number of arms, yes. Yeah, that's a very good question.
So n is the number of poles for arm I.
And it's the number of pulls for each arm. Yeah. For every arm, I just pull n times. Yeah. So that's why total number of samples is like n times the number of arms you have. So the proof is actually very straightforward, given all the mathematical tool we have learned. This is essentially by Hofstad's inequality. We know with probability greater or equal to 1 minus p over a for any fixed arm I, we have this r hat, subtract ri is less or equal to c prime some other constant times iota over square root of n. This is by Hofstad's inequality, because this is like a summation of independent random variable and independent random variable. And then finally, because we know by this choice of n, when we plug it in here, this is guaranteed to be epsilon. This is by our choice of n. Okay. So the first step is by Hofstad's inequality, and the concentration inequality, and second step is by our specific choice of n. We kind of like choose this n to be specifically to make this equal to epsilon. And then finally, we know this is for a fixed arm, and with probability 1 minus p over a, and we just do a union bound. Over all arm. We essentially finish the proof. That is, with probability 1 minus p, we have this. We have every arm. The difference will be less than epsilon simultaneously. That means the max I is also less than epsilon. Yes?
So we're able to just like ignore the lower order terms that usually come with Hofstad, or?
The question is whether we're able to ignore the low order term comes with Hofstad. I think Princeton has a low order term. Hofstad does not have low order terms. So there is no low order term here.
So what is the condition for epsilon optimal arm again?
Epsilon optimal arm again.
So like here, the epsilon optimal arm is because like expected RI.
Sorry.
So like, what's the condition of finding epsilon optimal arm?
I think this is slightly logic here. What I'm saying is once we achieve this, That is, my estimate for every arm is the difference of my estimate to the optimal, like to the true one is like less than epsilon. Then if we just pick the best arm, this is guaranteed to be epsilon optimal. I think I can specify a little bit more. So we're saying, let's say we define this I hat to be the argmax I of R I hat. So this is like after we have an estimate, we kind of like we pick the best arm according to my estimate. So what I'm saying is we are going to guarantee that R I hat is greater or equal to R I star subtracted by epsilon. So I'm say this, yeah. Once you have this guaranteed, you can make sure this is true. And the reason, do you want me to do a bit more calculation? I think we can easily calculate this. So what you can do is, so this is equivalent to prove that Ri star subtract Ri hat less or equal to epsilon, right? So in order to prove this, all we need to do is like we can do Ri star subtract R hat I star and plus R hat I star and subtract R hat I hat and plus R hat I hat and subtract R I hat. So all I did is like subtract and add a term, subtract and add a term. And we know this is less than epsilon. This is less than epsilon. Okay, probably we suffer some constant too, so we have 2 epsilon. And we know this is less than equal to 0. Because by definition, we know I hat is the optimal arm according to R hat. And so this I star is less than that. So that's why basically once we achieve this, we can find the 2 epsilon optimal arm. And you can like adjust the constant, like make this epsilon optimal by doing this epsilon over 2 or something. Okay, so essentially we have proved this is our sample capacity to find the epsilon optimal arm. And the second thing is we essentially want to convert this to regret. So with probability greater or equal to 1 minus p, the epsilon first algorithm has regret at most c times a t square iota over to the power of 1/3, where this iota is equal to log a over p. Okay. This proof of this query is basically by just doing the conversion we have, because this is exactly the explore then commit algorithm. So in the first phase, we already know the sample capacity is equal to this. That is c times some other constant, c prime, times, let's just use c, times a iota over epsilon square. Okay. And we can write this in terms of a iota epsilon minus 2. So we know this beta is equal to 2 in the applying the lemma. and we can bundle this entire thing together as this C in the previous conversion. So we know by lemma 2 or lemma 1, we know the commit, like explore then commit. Will give a regret that is 2 times this entire thing, C A iota of to the power of 1 over 1 plus beta times T beta over 1 plus beta. So we just plug in the beta equal to 2 inside, and then we kind of readjust the C to be some constant outside, like to be some other constant, and then this is done. Okay. So we just introduced a very basic algorithm. Basic algorithm is we kind of like we first do exploration, and then we commit to the best arm we find for the exploration. And we can think the exploration part, the sum of it is good, is 1 over epsilon square. But because when we do the computer regret, we're doing this two-phase, first explore, then commit. So our regret is something t to the 2/3. Okay. So you may wonder, this type of algorithm seems like a little bit artificial or inefficient in the sense that it can like divide everything into two phases. One is you first do exploration, and then you commit to the optimal arm. Like I think the first naive idea is you're thinking maybe I can just merge those two together, and this gives another algorithm called epsilon greedy algorithm. I think for a lot of practitioners nowadays, a lot of times, if you don't really know how to do exploration, like you have no idea what is good algorithm, I think the first go-to algorithm is still the epsilon greedy. Like because this is so simple, you can just always plug this epsilon greedy algorithm with any existing algorithm you have. So the algorithm, again, we will maintain an empirical estimate. We will use the same empirical estimate, R hat equal to summation j from 1 to nj r ni rij of ni. Okay, so this is the number of pools for RMI. And this is again like the random reward we receive for RMI at J's pool. Okay, so we just talk about the estimate. We haven't talked about the algorithm. So algorithm goes as follows: for t equal to 1 to capital T. So the major difference is we no longer do this two-phase. We first like put a random arm and then we commit to the best arm. In this epsilon greedy algorithm, we kind of like merge them together with some probability. So what we're saying is with probability epsilon, some small epsilon probability, I'm gonna pull arm a random arm, which samples from uniform over my action set A. That is, I'm just gonna randomly pull an arm. But this is only with some small probability epsilon. Otherwise, that is with probability 1 minus epsilon, I'm going to pull the greedy arm. I'm going to pull arm IT. That is equal to argmax of Ri hat. I. Okay. That is, so far I have pulled a lot of arms, and so some of them is picked by this greedy rule, some of them is picked by this epsilon, like random rule. And so I have some estimate. I'm going to use this existing estimate to pull the arm with the highest estimate. And so we can like either pull random arm with some small probability or with some majority probability, I'm going to just pull some greedy action. And after I pull this action, after I pull this arm, I'm going to observe RIT, which is stochastic reward I receive for the IT arm I pull. And I'm going to update my estimate. This is RIT hat. So you can think this is some variant of epsilon first, where in the epsilon first it's like I first do exploration and then I do commit. While here it's kind of like I do them like interleave with each other. That is, sometimes I will do some exploration, sometimes I will exploit by pulling the optimal arm. So it turns out this idea is basically just I will swap some order. Instead of doing exploration in the very beginning, I will sometimes do exploration in the later phase, sometimes do exploration, and sometimes take greedy action in the beginning. And it turns out this like swap in the order doesn't actually help much in the multi-bandit case. So in the theorem, we will also say with probability greater or equal to 1 minus p, the epsilon greedy algorithm still have the same regret. Has regret. That is O tilde to the A to the 1/3 and T to the 2/3. So hiding some log factor, this is exactly the same as the regret we achieve for epsilon first algorithm. So this proof is essentially also similar, very similar to the epsilon first algorithm. We will leave to homework 3. So this raises a very straightforward question, like whether can we achieve something, can we achieve some regret better than this, which can like achieve a better trade-off between exploration and exploitation. So it turns out the answer has been long known in this like bandit field, is a key idea called optimism. So called optimism in face of uncertainty. This is the principle And the algorithm we typically call the UCB algorithm, that is upper confidence bound algorithm. So we first talk about the high-level idea why this algorithm is like fundamentally different from a previous algorithm, and then we talk about the specific algorithm and the guarantees. So we can first summarize the previous algorithm. That is either epsilon first or epsilon greedy. It basically has two parts. The previous algorithm, essentially either you have exploration step that's going to pull random arm. And you have an exploitation step that is take greedy action. To maximize R hat. Like you do argmax I hat. So the epsilon first is like you first do a bunch of exploration step and then do exploitation step. While epsilon greedy is you sometimes do exploration step, sometimes do exploitation step. I think the bad part about the algorithm is whenever you do exploration, you do some random exploration. This is like inefficient in the sense it doesn't really leverage a lot of information we have. And so the key idea is how we're gonna combine exploration and exploitation together. So this algorithm, a previous algorithm just says sometimes I do exploration, sometimes I do exploitation. My combination is like a very naive combination, just like sometimes we do this, sometimes we do that. So a better strategy is instead I will compute a new thing that I tilde. You can think I tilde is something like I hat, which is my estimate. And plus some is like mean estimate. Okay, let's say mean estimate. Plus some bonus term, which talk about some confidence or randomness. Essentially, this bonus reflects our belief of the deviation between the true one. So you can think this R hat, R tilde itself contains both exploitation, if I just want to look at mean, and then exploration, because we will essentially add more bonus to the part of arm or the part of space we haven't visited so far. And I will essentially do an argmax of this I tilde. Okay. So in terms of multi-arm unbanded, this idea is very straightforward by UCB. For example, I have a multiple arm, like I have arm 1 and arm 2 and arm 3. So for arm 1, multiple different arms, and I have also pooled different samples. For example, arm 1 has a lot of samples here. This is like many samples I pulled arm 1 for a lot of times and received this reward, this reward, this reward. And for arm 2, I only pulled, like for example, this amount of time. And for arm 3, I pulled this many times. Okay, so the way to do this tilde and by this UCB algorithm is specifically like we not only have a mean estimate, which is this thing of each arm, but we also have a confidence interval estimate, or you can think this is like a mean plus or minus like multiple times standard deviation. So in this case, I'm saying my arm 1 probably is the optimal, like the true reward gonna fall in this interval. Well, for arm 2, because I only have 2 samples, I'm less confident. So I'm thinking maybe my interval is like this. My true reward is gonna lies in this interval. And for arm 3, and I have a little bit more samples, I'm saying the interval is shorter. And by UCV, upper confidence bound, essentially we're saying those intervals are my confidence bound. I'm gonna use the upper confidence bound, which is the upper side of the confidence bound, okay? This as my R tilde 1, R tilde 2, R tilde 3. And I'm just gonna pool according to the upper confidence bound. Okay. By upper confidence bound, we want to guarantee the property that R tilde is always greater or equal to I with high probability. So we want to have the property that my upper bound is, upper confidence bound is with high probability, a true upper bound of the true reward. Okay, so I don't like make any error. So this is like intuitive construction of the algorithm, and we will now talk more about the mathematical details of how we construct this R tilde and how we prove its high confidence bound. Thank you. Any questions about this high-level picture of the algorithm? So we talk about the formal algorithm. Of UCB, upper confidence bound. So the algorithm is actually very simple. The only different part is we will now, instead of maintain a directly mean estimate, we will maintain a so-called optimistic estimate. That is, we call this I tilde. It's equal to, first part is, again, the empirical average, j from 1 to ni, and rij of ni. This is the just empirical average. And then we will add a bonus term. So the bonus term is going to be depends on ni. Kind of like give us some confidence level of like how confident my estimate is. So you can imagine if ni is very small, that is, I only have like 2 or 3 samples, I have a small amount of samples, so I should add a big bonus to reflect I'm not very confident about this estimate. But if ni is very, very large, then I should think my estimate is relatively accurate, so I should add a small bonus. So in this case, our choice of bonus, in general, you can have a lot of different bonus choice. Our choice of bonus will make it to be C times square root of log AT over P over N. So the reason we choose this bonus will be much clearer later when we talk about why we want this type of thing. And once we make this choice, the algorithm is relatively straightforward. All we do every time is we just pull an arm, IT, which is equal to argmax I tilde. So we take a greedy action regarding to this optimistic estimate. And then we observe a new reward. And update. At tilde IT. I think another important thing about this algorithm is we see the previous epsilon first, epsilon greedy algorithm, we just do some random exploration. We truly just put a random arm. But here, by choosing different bonus, we can put in different prior or different knowledge about how we're going to estimate the confidence or estimate the randomness in this bonus term. So it kind of leverage more information than the previous algorithm. Previous algorithm just put random arm. Now we essentially we will prove this is essentially some standard deviation. We're using some standard deviation to help us better guide the exploration. In theorem 3. So we can actually prove with probability at least 1 minus p, UCB algorithm has regret at most square root of AT iota, where again this iota is some logarithmic term. Log AT over P. The most important thing is now we will observe that UCB actually have the square root regret. Probably has 2. Okay. Now it's a square root t instead of t to the 2/3. So this algorithm may actually strike a better balance between exploration and exploitation. So it actually has a better regret. So in order to talk about the guarantee of this algorithm, we just denote a few notations so that we're clear what we're talking about. We use this NIT to denote the number of times I has been put before round t. I think until round t. Let's see. So they include the number of arm, include if you put the arm at around t. And R tilde is the estimate of arm I at round t, at t's round. essentially we just use the same notation. Well, if we have a put t on the superscript, that means the quantity of my estimate or the number of times we have pulled this arm at t's round. So first lemma, we justify why we want to do this type of specific type of bonus. We can prove with probability greater or equal to 1 minus p that we have for all t, like all the number of all rounds and all arm, that the difference between my estimates average over NIT, j equal to 1 NIT R I j subtract I. This is essentially my mean estimate or average estimate at round t for arm I. And this is the true mean reward. We say this difference is less or equal to C times iota over NIT. And this is precisely our bonus, the choice of our bonus. Where again, this iota is equal to log AT over P. Very similar to the epsilon first algorithm, this is essentially also a concentration. The reason I say essentially not exactly the same is there's only one caveat. That is, when we apply the Hofstadter inequality, we usually just say, like for n sum of independent random variable. However, here this NIT, the total number of the summation, is also random. Okay. So because this NIT kind of denoted how many times I'm going to pull this arm I before round t. And this actually related to the random draw of the reward, because UCB algorithm actually depends on if you somehow happens to draw this arm with very, very high reward, and then I will pull this arm. And if you draw it with low reward, I probably will pull different arms. So the NIT is actually a random thing. So this seems like has some additional problem. But the good thing is we know this NIT is at most capital T. So it's from 0 to T. So it won't be like something wild or extremely large. So we can essentially use some martingale argument, martingale concentration, plus union bound, that the union over all possible numbers of NIT and to essentially address this problem. And this requires a little bit technical subtlety, and we will also leave this to homework 3. It's a very good exercise for the martingale concentration. But for now, it's okay if you don't understand how we're going to handle this technical subtlety, but you can just think this is like Hofting if an IT is fixed. And so clearly this bonus is a solid bonus. So this immediately gives the corollary that with probability greater or equal to 1 minus p, we will have that Ri tilde t, this is my upper bound, constructed upper bound of arm I at t's round, is greater or equal to Ri for all t in T and I in A. So this is why this is called upper confidence bound. This corollary is extremely simple. It's just because we're guaranteed our mean estimate, and the difference between mean estimate and the true reward is like bounded by this term. So all we need to do is like add this bound to the mean estimation to guarantee we achieve an upper bound. Okay, so we'll finally talk about how we prove the theorem 3, why we get a square root t regret. So the important property is like we guarantee this, our estimate is always with high probability in an upper bound, and we will leverage this fact in the theorem, in the proof of the theorem. Okay. So we start with the definition of regret, which is defined to be t, summation of t from 1 to capital T, that the reward of the optimal arm subtracted by the reward of arm I pull at t's round. The first step will immediately you leverage the UCB property, that we know the optimal arm, the reward of optimal arm is definitely bounded, upper bounded by the R tilde of optimal arm at iteration t, because we're guaranteed this is always an upper confidence bound for upper bound with high probability for the true reward, and subtracted by R IT. Okay. And the next step we'll actually use the property of the algorithm. We know at every round, the algorithm actually choose greedily respect to this R tilde t. That is, we will always choose the arm that maximize the R tilde IT. So that's why this is less or equal to R tilde t and IT. Because the way we choose IT is we maximize this R tilde and subtracted by RIT. Now we're in a very good shape because we look at our estimate at IT, and we like basically both reward are evaluated at IT at the same arm. So we say this is equal to summation t from 1 to capital T. We just plug in how we're going to estimate this R tilde. And we know R tilde is equal to the empirical average, IT, T, summation J It's a little bit complicated, but it's basically just an empirical average up to round t and plus bonus of n it t, and we subtract rit. And the good thing is I can actually swap those two terms. Like we first look at this empirical average, subtract RIT, and then plus the bonus. And by the previous, by the lemma 1, we actually know the empirical average, subtract RIT is again bounded by bonus. So we actually know this is upper bounded by 2 times the bonus of NIT. Which is equal to some constant times summation t from 1 to capital T NIT T iota. So finally, all we need to do is we calculate the very last term, and we just do very quickly. So all we need to do is we calculate the summation t from 1 to capital T, square root of 1 over NITT. Okay. The remaining thing is just some constant factor. So for this summation, I can do I can change the summation order. Instead of counting from little t from 1 to capital T, I can first count each arm. Okay, I first do a summation over each arm. And then for each arm, I'm basically just, we know for each arm is just 1 plus 1 over square root 2 plus 1 over square root t, 3. So it's a summation from m equal to 1 to NIT. Okay. So that is the total number of times we're going to pull till time t. And this is 1 over square root of n. So instead of counting from t, I'm counting each arm and how many times I pulled for each arm. And every time I pull each arm, I'm just adding 1 or 1 over square root 2 and 1 over square root t, 3, that kind of thing. And finally, we will use the inequality that is 1 plus 1 over square root 2 plus 1 over square root 3, till 1 over square root of n is less or equal to 2 times square root of n. So we know this is less or equal to 2 times summation I from 1 to a square root of NIT. And the final step is by Cauchy-Schwarz inequality. We get 2 times square root of summation I from 1 to a, 1 times summation I from 1 to a, NIT, where we know this is 2 times square root of a. Summation of 1 is equal to a. Summation of n is equal to t. Because the total number of arms, 10 times we're going to pull for each arm, sum together is equal to t. And this essentially finished the proof. Okay. This essentially wraps up everything we want to talk about for multi-arm bandit. In the next lecture, we will extend this UCB idea, optimism idea, to reinforcement learning and see how this idea will actually help us avoid the combinatorial log, the hard instance for exploration we talked about in the last lecture.